the organizer for this really beautiful conference and this nice place under very good weather as well. So, indeed, so I'm going to talk about integer control effects on complex manifolds. So integer control effects is a bit, I guess it's a bit simple as a model compared to many of the models that we've seen in this conference. But the point will be to show some mathematical results that could derive from this natural setting. And so as a disclaimer, I will just say that I will probably be very vague about the physical models. I will give some motivations first in order to explain where the general model comes from, but then the model will be really unspecified in the sense that it could be applied to quantum Hall effect, to the integer quantum Hall effect in some sense, but also maybe in other kinds of model that you could think of. So it's the point is really to try to give you some toolbox and maybe a beginning of a new general theory that could fit in this kind of models. So here is the summary of what I'm going to talk. So on the first point, I will discuss about the integer quantum effect in general. First on the plane, in order to give some insight on how it will be generalized on complex manifold, which will be the second point. Then I will recall a few details on the determinant apparent processes, which actually the probabilistic model which is hidden behind that, which is pretty well known in the case of the plane, but not so much in the case of complex manifold. And then I will discuss the case of such processes in the complex manifold. So I will describe some properties, and I will provide some limit theorems, so somehow a universality result about the correlation functions, and as well a large deviation property of a slightly more general process that could be seen as a kind of perturbation of the original process. So let's start it with a pretty simple model that I think everyone knows here, which is the integer quantum Hall effect on the complex plane. So you can imagine a system of electrons subject to a constant perpendicular magnetic field, B. And so for the sake of simplicity, we can just restrict to the first end state in the lowest lambda level. And we get this kind of wave function, which has already appeared in many talks here, and which can be still appearing in a slightly more general setting. And in fact, so as a tradition, the squared norm of this wave function can be interpreted as a probability distribution. So the question is, what is this probability distribution? And in fact, it's already well known that in this case, this distribution is also the same distribution as the eigenvalue distribution of complex Gaussian random matrices. So consider an n times n matrix whose entries are independent random variables with complex distribution with some variance related to the magnetic field, and indeed it can be proved that the eigenvalue density is exactly the squared norm of this wave function. And so this particular process is known as a determinant apparent processes, which is some kind of general model that was introduced by Odile Mackie in 1975. And the particular property, combinatorial property of such process is the fact that the endpoint function, so the correlation function, is the n by n determinant of some kernel, which is called the determinantal kernel. And in the case of the integer quantum Hall effect, it's actually called the G-Libra kernel, which has it has an explicit description. And in fact, if we let the number of particles tend to infinity, we obtain still determinant apparent processes, so which can be seen as not a system of particles anymore, but rather a general continuum density. And this is still a determinant apparent processes, and the correlation kernel is called the infinite G ensemble, which is actually some kind of general Gaussian, and which is somehow related to the Gaussian free field. So now the question, Oh yeah, and so so this kind of framework in the complex plane, which is reduced at its most simple case in what I've presented, is still actually a hot topic, and we've seen, for instance, in the talk from Yassine, but also many previous talks, that if you add some confining potential, if you consider some adiabatic transport, it's still a very, very interesting kind of model, and there are still a lot of research done in this case. But what I will present is another kind of setting, which is rather a simple setting in the sense that we won't consider really complicated potentials or anything like that, but rather we will consider just a space which is a curved space and which is actually in any dimension. So the formal setting that I borrowed from Michael Douglas and Semyon, I don't know if there is actually previous introduction of this setting in any dimension. I know that in the case of compact Riemann surfaces, there were also previous results, but in the case of any dimension, at least there is this paper that considers the case of a Kähler manifold in dimension D, so endowed with a Kähler two-form omega. And in this case, the magnetic field is represented by a two-form, which is the curvature two-form of some Hermitian metric on the holomorphic line bundle over the space. And so here is this curvature two-form. So you can express it as some two forms with respect to the norm with respect to the Hermitian metric on some local frame, which is a non-vanishing section of the bundle. And then we add one other condition, which is actually hidden behind the physical model, which is the pre-quantization condition, which is already well known from the let's say the geometric quantization from Costan, Souriau, and so on, and which is the fact that you require the Kähler form to be equal to I over 2p times the curvature of this line bundle. And in fact, you can also represent it as, well, at least the Chern class of the Durham cohomology class of this is actually the first Chern class of the line bundle. And so in this setting, we will consider actually the lowest Landau level. So we will replace the line bundle by its kth tensor power, and the idea will be to consider the holomorphic section of this new line bundle Lk, which has been already discussed a bit, for instance, in Benoit's talk or in Dimitri's talk. The fact that if you put the right conditions on your Hamiltonian, then you can consider that the eigenfunctions are always holomorphic section, and they are just eigenfunctions of the operator d bar. And so this space, so H0, the space of holomorphic section, is actually a finite dimensional space, which is a Hilbert space for some scalar product that is given here. So it's given by applying the Hermitian matrix to the sections and then integrating with respect to some volume form, which is expressed through the Kähler form. And so this is the space of the one particle function, and then if you want to construct the n particle wave function for free fermions, you have to take the Slater determinant of such functions. So you can take a basis. Typically, you can, for instance, take an orthonormal basis, and then so you get this nice n-point wave function. And the new question is the fact that, okay, so if we take the squared norm of this wave function, what kind of process do we get? Is it a known process? Is it still determinantal as in the case of the plane? And so a natural question is actually what happens when you let k tend to infinity, which actually corresponds to having a really strong magnetic field, which is actually the framework of the quantum Hall effect. And so I will describe a bit this kind of process afterward.
Maybe one quick question. Why would you wonder, of course it's determinantal, I mean it's free fermions. How could it not be determinantal?
That's a physicist answer.
No, but that's not, I mean, that's a rigorous statement. Any free fermion maps to a determinantal point process.
Well, technically, yes or no, because, I mean, how would you define the determinant of the well, let's see later, because the determinant of kernel is actually the Bergman kernel. So how would you define the determinant of such operator?
So take any free fermion system, you feel M states, you write the projector onto the M state, that's a kernel.
Yes,
that's a general.
Then how do you define the determinant of that? I mean, algebraically, how would you define that?
I can write a Slater determinant that's the same as you wrote here. I mean, what's...
Yes, well, actually, so maybe the question is how do you define a determinantal point process? Because here I agree that the fact that the joint distribution is written as the Slater determinant, but the fact that the Slater determinant gives the determinant of the reproducing kernel is actually non-trivial in this case.
Because so essentially the whole thing to assume, if you integrate over some particles, it still needs to be a determinant. That's the only thing. Yes.
Yeah, actually, you have to prove that.
It's based on the fact that it's a reproducing kernel that comes out for free.
Somehow, no, not because actually we always say that it's a reproducing kernel, but in fact it's not a reproducing kernel in the sense that we always see in the case of Hilbert space of L2 functions. Here it's a Schwarz kernel over sections of line bundles, and so all the combinatorial properties that use the fact that it's reproducing kernel are not trivial, because you don't consider when you develop your determinant, you don't consider product of functions, but tensor products of sections. So when you define your determinant, actually the determinant in the algebraic sense doesn't make sense. So you have to give some sense, and that will be the point of my next talk.
It's the exact same problem in two real dimensions. There's no other complications, and you would already face.
Well, actually, in the case of R2, it's just functions. So the product of functions is committed.
In genus 1, you would have the exact same problem.
Oh, you mean for instance for a compact surface? Yeah, exactly.
It's known that it's a determinantal. So
well, it's known.
Okay, say by
so
physicists.
yeah, it's known by physicists. And what is the purpose of my talk actually is to give a rigorous framework of a lot of things that might be quite known by you, but which were not necessarily well explained from some mathematical perspective. So I guess many things that I will discuss here are trivial for physicists, but let's say that from my mathematician's perspective, there were some blurry lines when you go from the case of the plane to compact surface or manifolds, and that will be actually the purpose of this discussion. So I hope that what I will explain afterwards will give you more insights on why I asked this kind of questions. But yes, in some sense for physicists, I guess it's pretty obvious. So let me start by some generalities on determinant point processes let's say in the probabilistic framework. So first of all, a point process, so it can be defined in two different ways. If you consider a locally compact Polish space with its Borel-Sigma algebra and some reference measures. So for instance, if you take RD, you can take the Lebesgue measure, or if you consider more fancy space, you have some measure that you could consider. And a simple point process is simply a random measure, which is the sum of Dirac measures on random points. Or you can also equivalently consider it as a random configuration, that is locally finite random subset. Or you could also consider this random subset as a random tuple up to permutations. So in some sense, you can imagine a random family of n points which have the property of having a symmetric density function. And the main object that we want to look on such points is the factorial moment measure, which leads to the so-called correlation functions. So its definition is a bit tedious. It's actually some expectation of a combinatorial sum of the product of direct measures. And so if this measure happens to have a density with respect to the ambient measure on the Polish space, then its density will be called the endpoint correlation functions, and which is the endpoint function that physicists always consider. So there are some assumptions to get that such correlation functions exist. It's not existing actually for any kind of point process, but for most of them it's the case, and it will be the case in many cases. And in particular, we have a result by Johann Stone, which gives that if you have a joint symmetric density, then you can compute the correlation function by successive integrations of this density with respect. So you take the nth marginal, and you have some combinatorial correction, which involves the number of particles and the number of points, of points that you consider for the correlation function. And so that will be the main tool that we will use actually for the determinantal point process, as we will see afterwards. So a determinantal point process, which is probably known by most of you, and probably all of you even, is such process in the case where the nth correlation function, with small n, is actually the determinant of some kernel, which is a kernel on the Polish space. And so it will be the main purpose of this talk. And we already have a lot of such examples of processes in the mathematics literature, and sometimes in the physics literature as well. So for instance, you have the eigenvalues of classical random matrix ensemble, so the GUE, for instance, or even the circular ensemble, or the GUE ensemble that I discussed before. But it's also appearing in the zeros of some Gaussian analytic functions. In the case of uniform spanning trees, so here it's rather on discrete spaces, because I will essentially mention continuous spaces, but you can also consider such processes, for instance, is in lattices and stuff. And another example of discrete determinant point process is the show measures on Young diagrams, which is really present used in representation theory, and happens, for instance, in statistical mechanics. If you do some directed percolation, it can sometimes show up. And one particular case of determinantal point process is actually the orthogonal ensemble, which is related to orthogonal polynomial with respect to some measures, which already appeared in a lot of these talks as well. So in this case, we consider a tuple of random variables which has this kind of density, which is somehow a kind of Slater determinant, or square of the Slater determinant, with some orthonormal family in the L2 space. And so it is well known that in this case, indeed, this is a determinantal point process with kernel given by some reproducing kernel of the L2 subspace of dimension n spanned by the orthonormal family, and which is called in this case the Christoffel-Darboux kernel. So there are a lot of such examples in physics. For example, the quantum-Maleshev flow, which was studied by Wigman, Zabrodin, Edenman, Makarov, and also, for instance, the random normal matrix model, which was discussed a bit by Yacine earlier. And in this case, well, so as I said, the kernel is called usually the Christoffel-Darboux kernel. Well, more recently, it has become also called the Bergman kernel, as we could have seen in some talks. And well, I guess that the explanation will come from later on. And so in this case, if the orthonormal family is a family of orthonormal polynomials in the real line, actually this kernel can be expressed using the celebrated Christoffel-Darboux formula, which expresses the whole kernel using only the last two elements of the family. And in this case, it's very convenient because you can just study the asymptotic of the kernel thanks to the study of the direct orthogonal polynomials, and then it leads to some kind of saddle point analysis and helps to obtain some very nice property of the scaling limits of this process. And so we have similar formulas for the unit circle, but not when you consider general measures on the complex plane. And in fact, when we don't have this formula, we have to rely on heavy complex analysis, again, as we could have seen, for instance, in Yassine's talk. And so the idea is to, okay, what could we do if we want to generalize that in manifolds? And so let me start with some reminders on the Bergman kernel on manifolds. So we consider a compact complex manifold of dimension d and a Hermitian holomorphic line bundle with a continuous metric that can be represented by a local weight phi. And so we consider as in the introduction the Hilbert space of the holomorphic sections of the kth tensor power of this line bundle. And so, as I already said, it's a Hilbert space for this inner product that I will denote by the brackets index k phi mu. So mu is a finite positive measure on M. Here we consider slightly more general model than the case of the Kähler model, because the finite positive measure does not necessarily erase as the measure associated to a Kähler form. So it's any finite positive measure. And then we consider the metric on Lk, which is just the kth power of h, which is represented by the local weight k phi. And so the Bergman kernel is the Schwarz kernel of the orthogonal projection onto this Hilbert space. So which is kind of a reproducing kernel, but with a slightly difference, which is the fact that it's described as a sum of tensor products of holomorphic sections of the line bundles and on the dual line bundle. So it's a bit more complicated as an algebraic object, in the sense that this tensor product a priori doesn't commute, and so one of the main questions, for instance, will be, okay, what happens if we try to define the determinant, let's say formally, or rigorously, because formally it's already well known, and I think that if I write this like that, everyone will be happy here, because indeed you can see that as the projector onto the orthogonal projector onto the lowest Landau level, if you want to think of the integer contour effect. So indeed, so for instance, if you consider a simple case with it, which is the case of the complex projective plane, and you take the hyperplane line, the hyperplane line bundle, then in this case, actually, we can show that the space of holomorphic section is equivalent, well, let's say isomorphic, to the space of homogeneous polynomial on C of degree k. So it's really a classical, well, a geometric generalization of the previous case that we discussed in the plane. And so before going to the description of the process, let me discuss a bit of the properties of the Bergman kernel, which are really nice and will be helpful actually to get some asymptotic result on the process afterwards. So if we assume again that the measure is associated to a Riemannian phone form, and that the curvature form of the line bundle is positive, so you can either think it as a positive 1-1 form on the manifold, or you can just consider locally that the Hessian of of the local weight is positive definite for every point of the manifold. And in this case, we have first a diagonal expansion, which is first due to Tyan and then Kathleen and Zeldich in the late 90s, which explain that you have actually an asymptotic expansion to all orders with smooth coefficients. And so we have the first coefficient, which is k to the d, and then you have decreasing integer powers of k, and you can go to any order that you want. Then you also have a near diagonal expansion that we will use later on, which was first discovered by Blair, Schiffman, and Zeldich, then reused by Schiffman and Zeldich, and generalized in slightly more general settings by Mine, Marinescu, then Berman, Bertson, Björstrand.
Sorry, what was K?
K, where? Oh, K is actually the power you take of the line bundle. So,
okay.
So yeah, so as I said, we consider the space of the homomorphic section of the kth tensor power of L. So here is where the k comes from. And so I didn't mention that, but so the space is of finite dimension, and I will denote that by nk, which is actually equivalent to k to the d, where d is the dimension of the manifold. So in some sense, for instance, when we consider the asymptotic expansion, we see that the leading term is of order nk, because it's out of order k to the d. And so in the case of near diagonal expansion, we consider a system of local coordinates in a neighborhood of some points, and actually there is a limit kernel such that the rescaled Bergman kernel with a rescaling length which is of order square root of k gives at the first order the limit kernel d infinity, and then all other terms of order k to the d minus 1/2. So we have half integer powers of k in this expansion. I only give the first one because it's the one that will interest me. But there is actually also an expansion at any order, which involves the same kind of objects as in the diagonal expansion, which are essentially some polynomials of the scalar curvature and the Ricci curvature of the manifold. And so the main question I will ask now, so it's a bit of the follow-up of the discussion we've had just earlier, is the fact that if you define formally the determinant of the Bergman kernel, so if we want to define it, we could do it by many ways, but let's say we want to do the Laplace expansion of the determinant. So formally, we do the Laplace expansion of the determinant. We just expand everything, and then in fact we have a sum of several tensor product of sections of vector spaces. But in fact, the problem is that every term of the sum belongs to a different vector space. So algebraically, this equality makes absolutely no sense. Hopefully, we can deal with that using duality arguments, because as we can see, it's already pretty obvious in this description. It's the fact that we have actually tensor products of pairs of elements of one Hilbert space and its dual. And using some contraction on these Hilbert spaces, we can actually canonically produce complex numbers from these tensors, and then transform this bunch of tensor products as just product of inner products. And that will be the main tool that we will use to define properly this determinant. So we have some kind of canonical isomorphism. So if you would take, for instance, any tensor product of, let's say, the fiber Lx times any vector space, let's say Hilbert space, and the dual space of L, and you take this kind of tensor, then you can use the contraction of Vx to Ux in order to transform it into the inner product that is corresponding to the Hermitian metric on the line bundle. And then so you can identify the dual element by an element of the primal, and the contraction you can implement it as an inner product using the representation theorem. And then you can just replace all these tensor products by products of inner products, and then in this case we get an equality which is completely rigorous. And so the main point afterwards is to let's say to be sure that this definition is robust to all the combinatorial tools that are usually used in the case of Christoffel-Darboux kernel. And in fact, it is the case. As soon as we have made this canonical isomorphism, we can just show that all the reproducing properties translate into such results, and we will have the nice theory without any hesitation. So now let me introduce the point process that we will consider, which is so exactly the squared norm of the wave functions that we considered, but as I said, a bit in a bit more general setting, because we integrate with respect to a positive measure, which is not necessarily related to a Kähler form, but still we take the norm of the square norm of the Slater determinant with respect to the Hermitian metric of on L to the k, and so a Slater determinant with respect to some orthonormal basis of our preferred Hilbert space. And so a nice example, which is probably the simplest one, is the case of the Riemann sphere. The Riemann sphere, taking the round metric and so we consider the Riemann sphere using its Kähler property. So we get back in the case of the integer conformal effect, and we can have a Hermitian metric on the tautological line bundle, which is related to the Kähler to the round metric, and then in stereographic coordinates we get this kind of process, which is now written in as it can be interpreted, for instance, as a Coulomb gas on C, because in the stereographic coordinate we just have some complex numbers, and in fact in this case it's related to another random matrix model, which is well known, which is the distribution of the eigenvalue of the product of one G-Nibber matrix and another and the inverse of another one with two independent matrices. And so it's a result that was studied by Krishnapur in 2009. And in this case, yeah.
In that case, K is the size of the matrix.
In that case, that's a good question actually. So K is still the power of the line bundle, and you can
show the matrices.
Yeah. So for now, let me just say that it's so take K. Sorry, is it's the power of the line bundle. So you can take the dimension of the space of holomorphic section of the line bundle, which is nk, and in fact you can compute easily nk, and nk is equal to k plus 1. So the matrices here are of size nk, which is k plus 1. So it's a bit of a different convention than the usual one in random matrix theory, but I mean it's just a matter of notations. And so the Bergman kernel in this case has an explicit expression, which is quite nice. And for instance, it happens to be just equal to k plus 1 on the diagonal, because the numerator and the denominator are exactly the same if you take z1 equals z2. And so in this case, for instance, the asymptotic expansion on the diagonal is just trivial. You just have one term which is of order k, which is k plus 1. And you can also play with the off-diagonal expansion by replacing z1 and z2 by z1 and z2 over square root of k, and see some nice scaling limit. And well, actually, this case is the one-dimensional version of the result on the complex projective space, which is the space used in most of the results that I presented earlier, or at least one of the proofs of these results were using the fact that any Kähler manifold can be embedded in some complex projective space and then use the Bergman kernel on this complex projective space in order to extract some asymptotic properties. So now let me state a few results on the asymptotic properties of such processes in this framework. So the first one is actually a universality result, and so we can consider the scaling limit of the nth correlation function. Now that we are sure that the nth correlation function can indeed be written as some rigorous determinant, and in fact, using the previous seen asymptotic expansion of the Bergman kernel, and if you control nicely the expansion of the correlation function, you can get some scaling limit which is actually so independent on the manifold on the first order, and so in fact. In the idea of the proof, so as I mentioned earlier, it's to show that everything that's used in the orthogonal ensemble indeed work, which is not difficult, but just a bit of formalism and a bit tedious, but really nothing special. And then plotting the asymptotic expansion of the Bergman kernel into this Laplace expansion and controlling the error terms, and show that everything is independent. And so what I will mention as well is the fact that we can prove a slightly more general result, which is what I did actually in my paper, is that we can replace L to the k by L to the k tensor with the trivial bundle with a continuous metric, in the sense that we can perturbate h to the k, the metric h to the k, by some continuous metric, and it will not change the scaling limit. And I mean, it's pretty expected in the sense that the continuous metric will be of order 0 in the terms of k, so it will not contribute to the scaling limit when you rescale it. And so let me mention that it's quite surprising, this previous result. Although the result is quite easy to prove, it's really unexpected from the random matrix perspective, because it's in the random matrix lore, it's always considered as very difficult to get some universality result. So it's really some kind of meta theorem that is some kind of Saint Graal for many random matrix researchers. It's saying that the scaling limit of the observables, so for instance the correlation functions, are related to the Gaussian distribution. So, and it's universal in this sense. So it's really the random matrix equivalent of the, let's say, central limit theorem. And to quote, for instance, Edelman, Guillaume, Péché, which are some specialists of this kind of questions, the universality is widely found in the field of random matrix theory. The universality principle loosely states that the eigenvalue statistics of interest will behave asymptotically as if the matrix element were Gaussian. So it's really a principle that is still a hot topic in random matrix theory in general. And the particularity is that for many models, even if the universality holds and the scaling limits are the same, often the tools used are very different, and it seems to be a bit like a coincidence, the fact that the scaling limits are the same. And in our setting, actually, the universality is almost free in the sense that it's a direct consequence of this universal kernel that emerges from the asymptotic expansion of the Bergman kernel, and so it can even be a bit relaxed actually if we consider, for instance, some singular metrics on complex manifolds. We can also get some let's say Bergman kernel asymptotics. The full expansion does not exist to my knowledge for singular metrics, and that's the real issue because it uses so it's particularly some results by Berman, which uses actually holomorphic Morse inequalities, which are using some pluripotential theory, and so it's really a much more analytic point of view than the one I presented, which is really more general complex analytic, complex geometric point of view. But still, there are some fewer generalizations where we can expect to have still such kind of universality. And so the process with this limiting kernel is actually the infinite Janibr ensemble if we take the dimension 1, and so it's a d-dimensional generalization of the infinite Janibr ensemble if we consider a general manifold. And so we really have the same scaling limit as the case of the plane. And so the intuition behind that is the fact that when we consider the asymptotic expansion of the Bergman kernel, in fact, we have this first term, which is using some Gaussian coefficients related to the Janibr ensemble, and the higher order terms involve the curvature, but not the first one. So in some sense, we don't see the shape of the manifold when we consider the scaling limit, and that's really, if we zoom enough, we don't see anymore the impact of the curvature either of the surface or the manifold, or of the curvature of the line bundle. And so let me finish with some slightly more general process, which is actually a perturbation of the previous one. So now we consider the same kind of random process, but instead we perturbate that with some potential V, which is taken continuous. And so we still get this later determinant with orthonormal basis for the scalar product given by k phi. So it's really with the non-weighted case, so that it's really not an orthonormal basis with respect to the whole weighted measure, but only with respect to the initial Hermitian metric. And so a particular fact which is already interesting is the fact that the partition function is now non-trivial, in the sense that in the previous case it's really well known that the partition function is just n factorial n, and in this case it's actually n factorial n times some determinant of the gram matrix of this time the weighted scalar product. By the way, there is a small mistake. It's not phi, it's k phi plus v. And so, this is not trivial to compute because the psi are orthonormal with respect to the weight k phi and not k phi plus v. And so now we cannot conclude anymore than that this process is actually a determinant apparent process. So, and it's probably not actually. It may be more related to what we could imagine as a Coulomb gaze, but still not a general Coulomb gaze, because we still have a power 2 here, so it would be some beta equal 1 ensemble, but with a potential. Yes?
So one quick question. So is your issue that the psi's are not orthonormal, but I could Gram-Schmidt them, that would not change the determinant?
So,
I mean, when you write the determinant of the Slater, it doesn't matter whether you take orthonormal states or not. If they span the same linear subspace, it's the same determinant, it's the same Slater.
yes, but in fact, the issue is that if you do the orthonormalization procedure, you won't be sure anymore that actually you're not sure that the Gram-Schmidt orthogonalized version will still be holomorphic. I mean, we do not assume V to be holomorphic.
It doesn't need to be holomorphic to be a determinantal point process.
Well, it will at least it won't be it might, well.
I would guess it is a DPP.
So in some sense it would be a DPP, but not the same kind of DPP, in the sense that you won't be able to write his reproducing kernel as a Bergman kernel. So it's, yeah, maybe in fact you can.
And why can't you absorb the V in the measure?
It's imagine if you took the Keylef in the metric, not.
Yeah. Yes, indeed. So yeah, it's indeed still a DPP, but we cannot use the same asymptotic result that we had before, because well, again, it won't be a DPP with respect to the Hilbert space of holomorphic sections. It will be a DPP living on some subspace of L2 of the sections, but not necessarily holomorphic sections.
No, they will be holomorphic. They just have different metric.
Why can't you absorb this in the mu, in the d mu?
Well, because okay, so what might not be clear here maybe is the fact that mu does not depend on k. If you let mu depend on k, then you won't have any of this this framework. And so as you have a power k in this perturbation, you cannot let mu depend on k. Otherwise, you won't be able to rescale. You really have to encompass the whole dependence on k in this density with respect to mu. Otherwise, I mean, you could still, well, I agree that it will still be a DPP, but you won't be able to see that as an orthogonal ensemble with respect to a non-weighted measure. Which is important. What is important here is really the fact that the ambient measure on the space must not depend on k, and so that's why we have to do this slight discussion that I will do afterwards. So yeah, apologize for these wrong statements, but still we can still get this partition function, which is nice. Which is actually we can see that as some cumulant generating function of the non-weighted process, because as I wrote here, it's actually so the exponential of minus sum of the v minus k. Sorry, there should be a k here. Minus k times v of xi with respect to the previous DPP density. And so I will still present some large deviation results, but let me first introduce some more objects. So first, let me define the Bergman measure as, so it's basically the measure on the manifold which has density given by the rescaled Bergman kernel on the diagonal. So as we have seen, the Bergman kernel on the diagonal has an asymptotic expansion, and its first order is of order k to the d, which is the same as nk. So this is of order 1, so we can easily show that it's a probability measure. And so there is a result by Bergman, which is that if we consider a weighted measure, so again we have some. It's a bit similar to the previous case, which is consider a weighted measure with respect to mu and with some local potential phi or k phi if we use that, and if it satisfies some technical assumption which is called the Bernstein-Markov condition, then the measures that I define here converge weakly in the sense of currents to some equilibrium measure, which is actually given by some complex Monge-Ampère equation. And so it's really in the sense of currents because the framework here is a bit more general than the one I considered, and sometimes these are not really, I mean, the limit is not necessarily a measure, but it's really a current. So it can be, so it's a distribution valued differential form. And so actually the Bergman measures in our case are actually the expected empirical measures of the process. So we get for free that the expectation of the empirical measures converge to this equilibrium measure. And in fact, using the previous result that we get about the correlation functions, we can strengthen this convergence in expectation and obtain actually a convergence in probability to the empirical measures, which is nice. And but now the question is, okay, can we get something from the weighted process? And I think it will be, almost two last slides. So
technically all the time, so let me.
Yeah, okay, sure. So let me introduce the equilibrium energy, which is some functional on the space of continuous functions on the manifold, and which is expressed through the equilibrium measure that I defined earlier. So it's functional defined by so that its directional derivative on the direction u is equal to the integration of u with respect to the equilibrium measure. And so if we go further into a variational approach, we can obtain the Mabuchi functional, which was introduced in '86 by Mabuchi and studied in particular by Donaldson in 2005. And so it's this variational version of the equilibrium energy, and it will be useful to define some function that I will call the rate function, which is actually the Legendre-Fenchel transform of this Mabuchi functional. So it's really it's this time functional on the dual space of continuous functions, which is actually the space of probability measures, and it's just the Legendre-Fenchel transform in classical convex analysis. And now I can state large deviation results, which is the fact that the empirical measure of the weighted process, so this time with v which is not necessarily equal to 0, it satisfies a large deviation principle with the function given by the rate function that I introduced before, and with speed which is k times nk, so it's of order nk to the 1 plus 1 over d, or equivalently to the k to the d plus 1. And so it means rigorously that for any measurable set in the Banach space of probability measures, we have these long inequalities of logarithms of probabilities. So which kind of means that the logarithm of the probability of having the empirical measures within these measurable sets are equivalent to the exponential to the minus infimum of the rate function. So it's some kind of exponential concentration of the events. And so classical result is the fact that in particular the empirical measure converge weakly in expectation to the unique minimizer of this rate function. So we get an equivalent result of this result, but we don't get necessarily the convergence in probability. We still need to deal with the variance. And so let me mention that there are some similar results in different settings that are due, for instance, to Bloom and Levenberg in 2013, but in the case of the complex space. And there is also a result by Berman in 2018, but for the unweighted process, that means it's only with v equals 0. But in a slightly more general setting, because he allows for metrics that are on the line bundle which are not necessarily continuous, and so which is a bit. And so let me finish with quick ideas of the proofs, which is the fact that we can relate the large deviations through the cumulative generating function using the so-called Gartner-Harris theorem, which is a really general theorem in probability theory, using this relation between the rescaled cumulative generating function and the rate function, which is so supposedly the Legendre-Fenchel transform of the rescaled limit of the cumulative generating function, which is so, and this function is displayed here in the case of in the case of a single random variable. And so in the case of empirical measures, we can write it as some logarithm of expectation with respect to the unweighted measure of the exponential of the linear statistics. And in fact, we can prove, using some results by Berman and Buxton, that the first derivatives of these cumulant generating functions are expressed in terms of linear statistics of the unweighted process, which is already known using the previous scaling limits. And so with the proper rescaling, we obtain the Mabuchi functional if we get the convergence of this rescaled cumulant generating function. And I think that's it. So thank you very much for your attention.
We have a few more minutes for questions. If there's any more. Simon?
I have one. So sometimes it's interesting to look at conditional processes where you say that there is some mass, maybe a particle at a point, and you look locally. Can you say something about rescale limit near such a point, or I think?
Well, would you mean that the whole mass is concentrated around one point?
Well, you say that you condition the process. You say that there is a particle at a certain point, and you look at the other particle near.
Yeah, you mean like sensitivity with respect to insertion or deletion of.
Something like that. Yes, exactly.
Well, I haven't found any result on that particularly, but it's something that I'm willing to look for actually, because I have some question about this kind of process, for instance, which is related to what is called hyperuniformity in math, but which is somehow the same thing as the area law in the case of physics. And I know that there are many results on such kind of processes in the case of Euclidean spaces, but not that many things in the case of manifolds. I guess there are some results in the sphere, maybe, but yeah, that's completely something that I would like to.
There are several results in the plane, actually also, so we can.
Yeah, in the plane, and even in higher dimension. I think in CD, I think there are some results, but in the case of curved spaces, I don't think that there are that many results. And yeah, that's.
Laurent Charles proved you have area law for all cumulants, for the fluctuations of particle in a smooth region.
Yeah. So you mean in the paper that you both about.
Actually, it was setting.
Actually, before your talk, I haven't heard about your paper, so I will really like to look into it later, because yeah, actually it would provide the whole case of dimension 1, which is already a huge step.
Any dimension.
Even any dimension, you consider any Keller manifold?
Any Keller manifold.
Okay, yeah. So I guess that answers to Yassine's question.
But not in your generalized setting. It's
yes, but yeah. So, but at least in the determinantal setting. So. Yes, questions?
My question is stupid, but this...
no stupid question, only stupid answers.
This B infinity was the same as in CN? It was the Berman kernel in
yes.
CN?
Well, almost. Actually, it's not completely the same. It depends on the assumption that we make on the curvature of the line bundle. But essentially, it's the same with some correcting term that might be involving the. I have to look for it again. But I think it might involve the eigenvalues. Well, the eigenvalues of the Levy matrix of the curvature. But that's the only special things that might involve. So if you do some assumption on the curvature. So that its eigenvalues are equal to 1, you exactly get the case of C to the D.
I see. So in terms of I was thinking in terms of the integer Hall effect. Basically, what this means is that as a Hall fluid, locally it all looks the same or something.
Exactly.
It's very interesting stuff. Okay, thank you.
Okay, maybe if there's a further question, they can be. Or is it one more?
Not sure whether it's a stupid question, But so you said that your determinant was ill-defined.
Yeah.
Maybe it can be given a good definition in another way. Maybe one should think of this Bergman kernel as a map from the tangent space over one point to the tangent space over another point. And if you call these points x and x prime, then you can visualize it as an arrow, and products are then well defined provided the arrows concatenate.
Exactly, and in fact, you can, for instance, consider that the Bergman kernel is actually some section of the external power of the line bundle. But then the question is, okay, so it defines very well the Bergman kernel. You can also define very easily the Slater determinant as a section of the determinant line bundle. But then, how do you relate both of them in the sense that if you square the Slater determinant and then compare it to the Bergman kernel, it's much less obvious that you can relate them in terms of combinatorial identities. So one thing that could be done, and that, let's say, didn't satisfy me, but maybe would be sufficient for most of you, is that you could just consider the quotient of all these spaces by the permutation of tensors. So in this case, I mean, I guess it could be well defined, but I mean, it's not that clear anymore that how you define these objects in these quotient spaces, because I'm not sure that these quotient spaces are still really line bundles over manifold, or maybe bundles over orbifold. I don't know. So it might be much more complicated in terms of objects, but it's also a thing that I tried to consider. And even if you take another definition of the determinant, for instance, if you develop the determinant as the product over cycles, you still have this same issue, because you have to permit the cycle when you integrate. And so as long as you permit, you have to make sure that it's commute, and it's not the case in the case of tensor product.
Okay. So maybe let's thank the speaker again.